Physics reaction video number 56. Today I tried something new. I think I typed physics example problems, which ordinarily would give a gigantic list of all kinds of who knows what. But if you filter for this week, man, you find the teachers. People are working hard. So I think that's working for me. Here we go.
Okay, so today we're going to take a look at the example problems for section 1. We're talking about periodic motion, which, if you recall, is the repeating motion, such as in a spring or a wave.
Mr. Kisling, call the high school office. Mr. Kisling, call the high school office.
Plus an announcement.
All right, now we did a couple of example problems for the lecture in class, and those example problems are laid out step by step in the lecture slides available in Canvas, so you can see those as well. These specific example problems that I'm walking you through are from your homework. The first one is from homework level 3, number 20, and the second is homework level 4, number 7, the last problem in the assignment. Let's dive in. So homework level 3, number 20 says, a spring that is stretched 25 centimeters from its equilibrium point experiences a force of 115 newtons. A, what is the spring constant?
All right, so how strong of a spring is this? So 115 newtons could pick up a 10, 11 kilogram object, so 25 pounds, let's say, so that'd be 3 gallons of milk. So string is stretched, so it moves 25 centimeters, so it moves this far, and it'd be like lifting 3 gallons of milk, so 3 gallons of milk before it finally is fighting back. That's remarkable. I don't know if I've ever seen a spring that can do that, right? So normally springs are these tiny little things that only move a little bit. 25 centimeters, what is that, about 10 inches? And quite a bit of force. So I'm trying to think what kind of periodicity that would have. I don't know if they're doing much periodicity in this, but 3 gallons of milk in one hand. I do it a lot. My family goes through milk like crazy. So carrying it from the car to inside. I've done 3 gallons of milk. Cool. All right.
Constant. And B, how much energy is stored in the spring? So if you recall,
I just want to pause and ask a question because I don't know that answer. I literally don't know the answer, right? So let's compare and contrast what she's done, which is show both A and B and read both A and B before starting. Option 1. Option 2, show but don't read. Option 3, only do the first one and don't even show the second one until later. Like, I can see huge value but doing it this way, right? Because you're like, okay, you guys were also going to need to do the energy, so let's not forget that. Just to like have the big picture in mind. Whereas other people, I think, might say, don't confuse, let's just focus and then see where it goes from there. So I don't know, it catches my eye.
Hooke's law equation says that the force acting on a spring is equal to the constant K times its displacement. Okay.
So some of you are having a heart attack because there's no negative sign there yet. So read this problem, right? It gives you a force, gives you a distance, it wants a K constant. The K constant is negative, never negative, right? So if you were to go the way she has it now, I don't know, maybe she'll add the negative sign later, right? But if you were to go with what it has now, you've got a force, you've got a distance, it'll be easy to calculate a K constant. And by not putting a sign in there, you're going to get the right answer, right? You're going to get whatever 115 divided by 25 is. What is that, 4.5? Boy, it doesn't sound that big. Did I do my math right before? Maybe it's 25 centimeters that's throwing me off. If you put in the negative sign, then you have to say, wait a second, but the force is actually acting the other way. So there's an extra negative sign that makes your negative signs go away. So let's watch to see what she does. But you know, I joked someone is having a heart attack, and you know, we have these approaches that we think are right. Why did I stop the video and start talking about it? Because I noticed it, right? Like, this moment of Hooke's law needs a negative sign. If you don't put a negative sign in there, it's wrong, blah, blah, blah. But for what she's doing, this is actually easier, I think. So let's watch to see what she's up to here.
And so if we write down what we know here, we seem to know that the force that the spring is experiencing is 115 newtons. And we also seem to know that the spring was displaced 25 centimeters from equilibrium. Now, here's the problem. We need these to be in meters. So to transfer centimeters to meters, we're going to take this decimal point and we're going to move it to the left twice, because centi is 100, which has 2 zeros.
Love it.
So 25 centimeters is the same thing as 0.25 meters. All right, now we can rearrange our equation. We are looking to solve for this guy right here, the spring constant. So if we say F equals K times X, and we divide both sides by K, we're looking for K, so we're going to divide both sides by X.
Awesome.
Those are going to cancel. Then we could say that the spring constant K is equal to the force that the spring experiences over the displacement that it travels.
Did you hear that? She said it's equal to the force that the spring experiences. That is exactly right. And you don't need a negative sign if you're doing that, right? The force that the spring experiences, as opposed to the force that the spring is providing or doing. Because that would need a negative sign. Oh man, I'm kind of fixated on this negative sign here, and how you don't need it for this problem. By the way, so thinking again, so 3 gallons of milk will stretch this thing 10 inches before it finally stops. So a spring that can stretch 10 inches and maintain its linearity, right, and not be like all banged up, is harder to find in the lab. Because, we're going to get a K constant that's just not that weird. It's going to be 4.5 or something. So 4.6 or something like that. Interesting.
Now, if we plug and chug our numbers, we can say spring constant K for this situation is equal to 115 newtons divided by 0.25.
Oh, you guys have been laughing at me. I didn't actually bother to do this, did I? Right? So it's whatever I said, 4.6 times 100. Okay. So this is a beefy one. This is a beefy one. So we have 460, something like that?
Meters. So that gives us a spring constant of 460 newtons over meters. Okay, now you may be wondering, you probably saw in the lecture and in the book that Hooke's law actually has a negative sign out front. It does, that denotes direction. For this particular problem, we are ignoring the handy dandy little negative sign. So we have a spring constant of 460 newtons per meter.
Oh, that's awesome.
Okay, that solves part A. Part B says, okay, if that's the spring constant, how much energy is stored in the spring? Well, if you remember from the lecture or from your reading, the potential energy stored in a spring is equal to 1/2 times the spring constant K times the spring's displacement from equilibrium squared. This might look a little bit like our kinetic energy equals 1/2 mv squared from chapter 11.
All right, so let's see if this is more or less than than the energy it takes to lift 3 gallons of milk 25 centimeters off the ground. So that is just mgh. So we've got we've got about 10 kilograms times 10 is 100 times divided by 4. That's about 25 joules, right? 25 joules. This answer is going to be 460 divided by 4 twice is 140 divided by another 4 is about 35 divided by 2 is about 17. So what did I say before? I've already forgotten. 25, 17. Yeah, this will be less, right? So it'll take less energy to stretch this sucker out than it would lifting it from the ground. Why? Because gravity has a constant force, whereas the very first part of the spring, super easy. It's only that last little bit. In fact, it's only the very last moment when it finally has the same strength as gravity. So I would expect less.
Good, because then we've already practiced things like this before. Okay, so 1/2 spring constant times displacement squared. Let's write down what we know, okay? 1/2 is a constant. We know from part A that our spring constant K is 460 newtons per meter. And we know from the initial information given that the spring was displaced by 25 centimeters. We need that to be in meters so that our units will cancel. So we're going to convert that to meters by moving the decimal place, 0.25.
So that was really interesting, right? I mean, it's literally right up here. So she could have said, "Oh, it's right up here. Let's go." But she's got a scaffold, right? You write what you're trying to calculate, you write down what you know, and you constantly fix the units. So from that scaffolding thing, it kind of makes sense to put it down again. I wonder if she's going to say anything about just like what we did before or something like that. But from a pattern, hey, you guys, here's a set of things that it's always going to work for you. Do this, and you'll have confidence that you can calculate these things. So I thought it was interesting that she did it twice. Frankly, I just assumed she was going to just write this down. But she has this way of saying, hey, write down, make sure you know everything before you start plugging it in.
5 meters. And that's all that we need to solve this problem. So let's plug and chug because it's already solved for potential energy. So the energy stored in the spring is equal to 1/2 times our constant, which was 460 newtons per meter, times our displacement, 0.25 meters, and that is squared. Now recall, when you square this, you're going to square the number and the unit. So let's go ahead and apply that square, okay? Potential energy equals 1/2 times the constant.
I like this.
Times 0.25 squared is 0.0625. And meters squared, because we also square the unit.
That's really
Okay?
cool. I like that a lot.
So now if we multiply everything out, so we take 0.0625 times 460 times 1/2. Okay? We are going to get a potential energy of 14.4. Now let's look at our units. We have meters on the bottom and we have 2 sets of meters on top, so that's going to cancel 1 set of meters.
Cool.
Okay, down here, so we are still going to be left in a Newton times a meter. Okay,
Also
remember
known as-
this Newton is on top of the fraction up here. It's a numerator, and this is, we're going to pretend this is over 1, so you're going to multiply the meters by the newtons. So a Newton times a meter. And if you recall from chapter 11, a Newton times a meter is the same thing as a joule, so 14.4 joules. And that makes sense because energy is measured in joules.
So I've got a sort of an arithmetic thing going in my head. 14.4 is an incredibly popular number, right? Because 144 is just 12 squared. So this is 12 squared divided by 10. And 46 is not a number I would normally associate with something that's going to land with some 12s in it, right? So it's really interesting that something with a 46 in it, or a 4.6 or a 460 ended with something that it just seems to have 12s in it. That's fascinating. All right, this was cool. I think I'll stop here. It looks like she's got time to do another one, but we'll stop here. Really, really interesting scaffolding. Loved the stuff about the sign. In fact, she came back at the end and talked about, oh, well, your book has this sign. That was super cool, and I'd love to hear your thoughts about that. Just really cool stuff. I loved this unit stuff at the end. Super, super careful about it being squared. That was awesome. All right, everybody. Have a great day, and remember, physics teachers are awesome.